So we've looked at how we can graph a complex number on an argand diagram or an argand plane using rectangular coordinates on the real axis and the imaginary axis, just using points x and y. And then we've looked at how we can express our complex number in a different form called polar form. And so now what we're looking at now is just a way how we can convert from one to the other. We've seen how we can express the distance from the origin to the point P using Pythagoras' theorem, and that's our modulus, and how that we need to describe the angle from the positive real axis to that line from the origin. And so what we're going to do now is run through a few examples. Now the first example we've got here is our 3 plus 4i, and we need to express that in mod arg form or polar form. Now we can find our modulus fairly easily using Pythagoras' theorem, and here is our formula. So our modulus r is equal to the square root of 3 squared plus 4 squared, and we find then we get the square root of 25, which is 5. So that's our modulus, nice and easy. Now to find our angle or our argument, the first thing we want to do is to establish which quadrant the complex number is in. Okay, so we can have a look at our values for x and y, or our real part and our imaginary part, and if we just do a quick sketch, it's handy. We can see whereabouts it lies. So if the real part is positive, we know we're on the positive real axis. Our imaginary part is positive as well, so we know it's going to lie here in our first quadrant. Okay, so then finding our argument is really easy. It's just our basic angle, which is found by finding arctan, or the inverse tan of 4 over 3. Okay, and then just putting that into our calculator, because there's no nice exact value for that, we get an approximate angle of 53.13 degrees. And so we can then express our complex number 3 plus 4i in polar form as 5 times cos 53.13 plus I sine 53.13, or more simply as 5 cis 53.13. So let's have a look at a few more examples. And we've got here 4 minus 4i. Our modulus r, we can find again square root of 4 squared plus negative 4 squared. It's going to be 16, and 16 is 32. Simplifying that surd, we get 4 times the square root of 2. So that's our modulus. To find our argument, let's look at the quadrant. Okay, drawing a quick sketch, we can see that we've got our real part is positive, so we know it's here on the positive side, but our imaginary part is negative, so now we're looking at the fourth quadrant. Okay, so now this means that when we're determining the argument, we need to use the appropriate angle. Now we've already said that our standard or conventional range of arguments are between negative pi round to positive pi. Okay, it's got to be in that region there, from negative pi right around to positive pi. Now because our angle is in the fourth quadrant, we're going to make sure that this angle fits within this range. So the easiest thing for us to do is to think, alright, here on this side is 0, so rather than going around all the way to there positively and then around again, that's going to be pi plus another pi on 2 plus this angle here. That is bigger or outside of this range, because our starting point is negative pi going around to pi. So the easiest thing for us to do is to think starting at 0 and subtracting this angle. Okay, so if we work out our first quadrant angle, our basic angle, and subtract it from 0, that's going to give us our angle in here. Okay, that's going to give us our angle. So we just need to think that is 0 minus the basic angle. And we do that in this way. That's why we're just going to ignore our negative that we've got here. Okay, so we write it as 0 minus arctan of 4 over 4, which is 1. Okay, negative arctan of 1. Arctan of 1 we know is pi on 4 radians, so we write our answer as negative pi on 4 radians, because it's 0 minus pi on 4, which is negative pi on 4. Therefore our angle theta is negative pi on 4. Then to write our polar form, we have 4 minus 4i. That's our given rectangular form. That's equal to our modulus, 4 root 2, times cis of negative pi on 4. Okay, our angle theta is within this range. That's using that form. We could also have written it in Euler's form as 4 root 2 times e to the power of negative pi on 4i. Or we could use polar coordinates, which is less commonly used. Polar coordinates are written with square brackets rather than parentheses, so that it doesn't get confused with regular Cartesian coordinates, okay, where we know that this first number is our modulus, our second number is our angle theta. Okay, 4 root 2 and negative pi on 4. Another example we've got is negative 1 minus root 3i. So we're going to first of all mark in where it lies on the plane. Negative 1, our negative real axis here, across negative 1, and then negative root 3 is our imaginary part. So we're going across to the left and down. We know it's going to be in the third quadrant. Our modulus r is found by finding the square root of 1 squared plus root 3 squared. So that's 1 plus 3, which is 4, and the square root of 4 is 2. So there's our modulus. Now to find our argument, we need to get our angle going this way. We can't use this way because that's going to be outside our range from negative pi to pi. So we want to go back this way. That's going to be our angle theta that we need to use. So in order to find our argument, we start at negative pi and then add our angle. So argument z then is negative pi plus arctan of our imaginary part over our real part, ignoring the negatives. Root 3 over 1, or root, which is root 3. So negative pi plus arctan of root 3 becomes negative pi plus pi over 3, and working through that we can see that that's going to be negative 2 pi over 3. So there's our argument corresponding to this angle here, which is within that principal argument range. Therefore the complex number negative 1 minus root 3i can be written in polar form this way: 2 cis negative 2 pi over 3, or using Euler's form 2e to the negative 2 pi over 3i. Or we could express it as in polar coordinates 2, 2 pi over 3. Looking through at another example, negative 3 plus root 3i. our modulus r, the square root of negative 3 squared plus negative root 3 squared gives us 9 plus 3, which is 12. So the square root of 12 simplifies to 2 root 3. So there's our modulus. In order to find our argument, we're going to find out where it is, which quadrant. Real part is negative, imaginary part is positive, so we know it's in the second quadrant. Now we can go from 0 round to pi here, so that's nice and handy. And our basic angle, remember, is in the first quadrant. So what we're going to do is going to go pi and then subtract our angle theta. And here we have pi minus arctan of 1 over root 3, ignoring any negatives. So it's pi minus pi on 6, which is 5 pi on 6. So that's our angle there, 5 pi on 6. So we can write our complex number, negative 3 plus root 3i, in polar form as 2 root 3, our modulus times cis 5 pi on 6, or using Euler's form, 2 root 3 times e to the 5 pi on 6i. We could also express it in polar coordinates as our modulus 2 root 3 and our argument 5 pi on 6. So go through those examples again, make sure that you're clear on them, and then you can work through exercise 3D of the textbook. Okay, thanks for watching. So what I've got up here on the screen now is just a polar grid. What you can see here is a polar grid. It hasn't come out quite as well as I'd hoped, because we can see that the x-axis is not shown. But just imagine that there is an x-axis going across there. Okay, there's our x-axis, and here's our y-axis, so our real axis and our imaginary axis. And we have our complex number, which we did on the last example, negative 3 plus the square root of 3i. The polar form of that being 2 root 3 cis 5 pi on 6. So to represent that on our polar grid, which is still a form of the Argand plane, we have 2 root 3 is our distance, and our angle is 5 pi on 6. So we know we've got to go around here to 5 pi on 6. Now this here is going to be pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, 5 pi on 6. So we know that this line here, that's our angle, and we have to go out 2 root 3 units. Now we can see, we can still kind of use our rectangular coordinates, because that's going to help us to get our position. Negative 3, okay, across here there's a negative 3, and up to the square root of 3, which is about 1.73. But we know anyhow, if we go straight up from negative 3, it's going to hit here right on our angle that we want. So that's the angle. I'll choose a different colour pen. Go for blue. Okay. Alright, so that's our distance there, and our angle there of 5 pi on 6, and our distance of 2 root 3. So that's it marked on the polar grid that we have. Okay, so here we've got another graphical representation of our complex number, just in polar form. Okay, we don't need to show this distance. Okay, it's really this point that we're interested in. It just needs to be on that angle. Okay, if we were to mark it using polar coordinates, then it's going to be 2 root 3 5 pi on 6. So that's done, and we've finished going through that.